Hi everyone. Today I'm going to give you a quick guideline of database design models. This is a list of the history of data models starting from file system, hierarchical network, and relational data model. From these points, we can think, hey, this is a real database. This relational data model is still very effective, although since the mid-1980s, object-oriented paradigm has been introduced. Some DBMS migrated or included new features of object orientation. So together with the relational database, if we add these together, object orientation and relational, and then make it feasible, then we call that object relational model. Currently, SQL, Oracle, they're all in this layer. This is a mainstream of standard database models. Meanwhile, since 2000, early 2000, then unstructured data has been available. For example, if you think of web data is not there's no format at all, right? It's not structured. So issue is how can we handle such data like documents or media using database management systems. So XML models or NoSQL data models, those data models has been introduced. In this slide, the running example is about college database where there are students, course, transcript, faculty, etc. The database that everyone here is familiar with. Okay, so if we think of a hierarchical structure, then it'll be like this. Say this is a course title, course description. Hierarchically, to that course, there's a meeting date, meeting location, and then CRN number. That also can be formed over department and also faculty as an instructor or student ID who are enrolled in. So this is a hierarchical data model, but has not been practically implemented, not widely used. And then network models also introduced. So if we see department and faculty, and then there is department and faculty are related, and department and students also related, students and class and faculty. Somehow they are linked, okay? So this type of network data model also introduced. In early 1970s, CAD in IBM, Almaden Center, that is in West Coast, developed relational data models and has been implemented in solid way. So we know relational database model, and this relational database model has been supported strongly by ER diagram. In order to build DBMS, then database should reflect the real world. So we have to first analyze the real world. What is the efficient way of analysis of the real world? There are many ways, but one of the most effective the method is entity relationship diagrams. Based upon the diagram, there is an analyzer produce ER diagram based upon the interviews and investigation about the real world data. And if we see the ER diagram, then everyone can see the same and understand on the same. It'll be the same, the exact same understanding. So that is the strong features. Okay, whoever drew the ER diagram, the interpretation of ER diagram remains the same. So we can ensure that the analysis really reflects the real world. We can verify it, we can prove it, whether the ER diagram carries over the real world. That is very nice, right? So ER diagram was first invented by Peter Chan when he was in a PhD student at Harvard University. And he became famous only because of this ER diagram. So department ER diagram has diagram because this is a diagram. It has a square and diamond. Square is an entity set and diamond is a relationship set. So in this case, the department, the entity set, you can simply think of the table. So department table, and then faculty table. If we see the department table and faculty table, then there is a relationship. Faculty here, there's a faculty members, and department has multiple department. Some of the department, some of the faculties may be also affiliated with this department. Some other faculty members may be affiliated with the other departments. But anyway, those affiliation is a relationship, because we have multiple relationships among the element in this department and the element in faculty, so that we call that relationship set. So relationship set can be represented in this ER diagram as a diamond. Okay, so we have also department and students. Then students major, a department. If a dual degree, multi-degree is permitted, then one student can major 2 department. And also students and class, then students takes a class. And if we see class, then class has multiple students. Similarly, we have a class and faculty, then faculty teaches class, right? A class can be taught by a faculty. Some cases there may be team teaching method is available, then one class here in this element and 2 faculty may be related. In that case, there is a team teaching. So we can represent that here and there a lot. Not only this, but we have here some of the participation constraints, mapping constraints, and more maybe added into these simple ER diagrams. Okay, we don't do. I think right. Modeling is important, but in this graduate program, we don't do much. Okay, we simply see, and also for the cybersecurity purpose, the modeling, understanding modeling is enough, but anyway, we'll do one simple the exercises. I'll give you short homework assignments, but I think that much is enough. Some universities, some department spend several weeks, maybe 5 or 6 weeks, the modeling only. Okay, like business school, but we don't do much here. This is another way of similar things can be defined and represented in a little different ways of interpretations. So departments, faculty affiliation remains the same, and the department offers a class. So class is more related with the department. In the previous class, not directly related with the department, but some cases, hey, we want to represent the relationships between class and department. Then you need to put here another diamond, and then you need to link them. The matter is here whether we want to represent that, and therefore we have eventually the tables. If it is a table, then we have a rows and columns. Then say 100 classes are offered from or by 10 departments. That kind of scenario, if it is important, then we have to represent that here in the model, and therefore in real database contains the data in details. So in this case, class here, and then class and students enrolled, that appears here, students and class, right? That is the same. And then faculty and students, directly there is advisement relationships. But earlier, student and faculty, there is no direct relationships. Only students may be able to see the faculty through the class in this ER diagrams. So depending upon the ER diagram, our interpretation may be slightly different. In that way, the way of building or creating a database that leads to different interpretation. Then how do you choose which one's better? One is better in some context, while the other one is better in another context. Or I would say, if we have a user model, how do we use this database? Depending upon the user model, sometimes this model is better than the other. Use, in other words, maybe service, right? So what kind of service are we going to make or provide? What kind of customers that we have? Even from the same the college database, our client is, for example, student, then the model should be modified to serve the students in an efficient way, rather than, for example, from the same college model, the customer client may be maybe course, okay, the course registration or transcript. I would say course registration. Then that should be different from the other earlier case, right? So rather than saying this is better or the other is better, but we should say that we need to make sure the model supports a use model. So my database model should support fully, efficiently a given use model or service that we want to provide, depending on who receives our services, our client. All right? That is ER diagrams. So ER then is nothing but a set of tables, right? Some description about table means there is a relational schema. So relational database can be designed starting from analysis. The outcome of analysis is conceptual design, so that we have ER diagram like this. That ER diagram now converted to a table. See, if we have this kind of ER diagram, then we have 3 tables obtained: students, course, and grade, right? Think about that. This relationship is not converted to a independent table. Any information about this takes is appeared in somewhere here. For example, students takes course. Then we have a student here, student ID. Course. Oops. It doesn't take. Yeah. So student takes course was appearing here. Students and CRN, therefore, who takes what, right, can be represented. And then students receive some grade, that also appears here, a grade. And, right, somehow this relationships can appear here. If we see this students and course, 2 tables, then they are not really related, right? There's no point that we can see the related. Student is its own independent table, like a course. Course exists by itself without having to include the students. Similarly, students exist by itself without considering courses. So they are not related unless we have this grade table. By having this grade table, finally, then students and courses are related. See here, this student takes that course, another student takes another course, right? That type of things can be represented. So from this ER diagram, then we have this kind of 3 tables obtained. Students admin transcript, then student and admin. Students request a transcript, and administrator can see the transcript. This is yet another specific data modeling. Assume this modeling is appropriate because there is a specific use models, specific clients. Therefore, students and administrator, right? Student and administrator, they are independent tables. But we have a transcript here so that we see CWID and CRN. Yeah, students can request this. Admin, in this case, are not really related, right? View is not shown here. So that in this case, I would say view may be in another table. And therefore, so admin name and then transcript CWID. So this admin and then here date, timestamp. So we may have a record, for example, Dean of Liberal Art looked at specific student records at a specific time. And another person also look at another students at another time. We may have that record appears here, right? It's another table. So view will be a separate table in this case. But this student's request to transcript, that should be also in that way. So we have request. See here, similarly, student, this is admin name, right? This is a student name. And then CRN, students can see specific course grade at the time. So this student's request some transcript data about the specific course at the specific time. In the previous, this takes relationships or some information about this relationship. This is represented in one of those records, right? So they are represented by this grade. So they are related. But here in this case, students, admin, and transcript, they are all independent tables. Therefore, this request, this diamond, is converted to its own table. This diamond also converted to that table as well, right? If we see the previous, this diamond disappeared because diamond is observed into one of the tables. We don't need to have this. If it is needed, then we have to make its own separate table. As I said, it depends on the use models. How can we use? What is the requirement of use? Okay, to support that user requirement, then we need to do in this way. And then object-oriented models started in 1981 throughout the whole decade of 1980 and 1990. They have been talking about this, right? not well implemented, not well commercialized, mainly because there is a implementation issue and language issue. In relational database, there is SQL language. That is very, very easy to use, very convenient, right? But in object-oriented model, modeling itself is very, very useful, but the user, if user wants to access the object-oriented database, then SQL language is not enough, because in this object-oriented model, we have to jump one table to another table, another table. There is a path expression is required. That path expression is not path expression. Then by itself, it is a language about how to traverse from one record to another record. Something about how needs to be written in object-oriented data models. But SQL, which is a language for relational database, SQL does not express anything about how, but it expresses what only. I wanted to see the difference, the language used by, for example, toddler, or maybe 2 years old or 3 years old, small kids who do not express all detail request, but still wants to request something. In the case, they say only, hey, I want to what, right? They want to describe, hey, I want this, I want that. They don't say, hey, I want to buy this. For example, go to the mart and there are multiple similar items there, but I want to choose based upon this criteria. They don't say about how. What I mean by that, if we can express what only, then our request expression becomes much, much simpler, because we don't need to worry about how, right? We simply express what I want. Here is what I want. All details about how to get it, that is handled by DBMS. I don't care. I want to see only what I want. All details about how to do, some methodologies, some algorithms. That is what I do not want. That is our system can do. Okay, so object-oriented model somehow needs all the time about how, not only what, but also how. So language-wise, that is a weak point. Not many people would like to use. Language is the tool that user wants to use to access, right? But if the language is complicated, then user do not want to use. That is a weak point. Representation-wise, object-oriented, that is perfectly fine. That's much better than relational database. Much, much better than relational database. See here in this ER diagram, this doesn't say about, for example, any operations not here, right? Any rules, any restriction, any constraints, any consistencies. Those all are very, very important issue in databases, but nothing handled in this ER diagram. But if we see object-oriented model, it can be represented. So in representation-wise, very, very powerful. But in language-wise, very, very weak. Therefore, object-oriented model is not really succeeded. Okay? And then after that, they developed, they combined the object-oriented and the relational database together, right? I want you to read that. And then finally, we can think of unstructured data models. If we use XML or NoSQL, then it could be possible. All right, I believe this is the broad understanding about the database models. Okay, so details, I want you to see it. And of course, I will ask you to develop relational database, all right, as a homework assignment. All right.